So in this presentation, we're going to look into Coulomb's law and understand Coulomb's law so that you can calculate the magnitude and direction of the force on a positive or negative charge due to other specified point charges, and analyze the motion of a particle of a specified charge and mass under the influence of the electrostatic force. So let's take a look at Coulomb's apparatus, and this is who discovered the law of force between two charged particles. So this design was set up so that Coulomb discovered that the force between two charges decreases as the distance between the charge increases. So one of his observations was that the force exerted between two charged rods is inversely proportional to the distance between them squared. So after taking a lot of measurements, he found that the force is proportional to 1 over r squared, where r is the distance between the charged rods. He also discovered that there was a directly proportional relationship between the amount of charge and the amount of force. So his second observation was that the force is proportional to the amount of charge. And since we have two objects that are charged, then that's represented by Q's, Q1 and Q2. So if we increase Q1 by 4 times the amount of charge, that means that we would increase the force by 4 times. So put together, Coulomb's law is that force equals K times Q1, Q2 divided by r squared. This should look familiar to Newton's law of gravitation, which was the force of gravity equals a gravitational constant times m1, m2 divided by r squared. So in this case, with static electricity and electric charges, instead of mass, we have two things that are charged. The distance still, as the distance increases, it still decreases the force. And we still have a constant here. The constant is equal to K. And K is equal to 8.988 times 10 to the 9. So it's a really big number. The units are, for the constant, are just so that the units cancel out and we're left with newtons per force. So those units are Newton times meter squared over c squared. So we could round this to 9.0 times 10 to the 9 Newton meter squared over c squared. So Coulomb also realized that the forces exerted by two like particles, two like charges, exert in opposite directions. And the force exerted between two charged particles with opposite charges exert in the same direction. So we can see that there's subscripts that we're going to use for force. Because it's an interaction, the force is an interaction between two charged particles, we're going to use subscripts to denote the different charges that are interacting. So in this example, the first one, we have charge 1 and charge 2. And So the force on the left, the force on charge 1, we say that's the first subscript, the force acting on charge 1 by charge 2 is how we're going to write our subscript. So this is going to help us keep track of the charges that are interacting. So the second force on the right, we have the force exerted on charge 2 by charge 1 on the right-hand side over here. Let's take a look at a conceptual example of two charges. So an electron and a proton, initially separated by a distance d, are released from rest simultaneously. The two particles are free to move. When they collide, they are A, at the midpoint of their initial separation, B, closer to the position of the proton, or C, when they collide, they're closer to the position of the electron, the original position. So when they collide, are they at the middle? Closer to, when they collide, closer to the proton, or C, closer to the electron. So think about what you think the answer should be. And the correct response is B, closer to the position of the proton. Why is that the case if they both have the same amount of force acting in opposite directions? Why do they end up somewhere closer to the proton? Why don't they end up in the middle? So come up in class, come up with your answer on Monday. Why is B the correct response? In our next example, we're going to take a look at a numerical example, computational example, of an electric force on an electron by a proton. Determine the magnitude of the electric force on the electron of a hydrogen atom exerted by the single proton. Charge Q is equal to positive charge E. That is its nucleus. Assume the electron orbits the proton at its average distance of r equals 0.53 times 10 to the negative 10 m. Your first question might be, what is this positive E? We didn't talk about that yet. We brought it up in class on Friday, just briefly though, that the charge of a proton is positive and the charge of an electron is negative. We denoted those positives and negatives. So if this is the proton, this is the electron. Remember that the proton has a charge of +1. That was +1 E. And the electron has a charge of -1 E, where E is an actual number, and it's the amount of charge that the electron has. So that's a really small number. E is an elementary charge. Because all charge is made up of electrons and protons, it is the smallest charge that exists. So E is a number that is equal to 1.602 times 10 to the negative 19 coulombs. So that's a really, really small number. The charge can be quantized, meaning that anything that has charge is a multiple of this number. Because E is so small, though, we normally don't notice this discreteness in macroscopic charges because it seems continuous to us. The charge does. So in reality, though, the charge is multiplied by some number depending on what the object charge is. So a proton has a charge of positive E. Electron is negative E. And we know the distance apart is R equals 0.53 times 10 to the negative 10 meters. So the magnitude, we're not worried about direction here. We're just worried about how much. So the force is equal to K Q1 Q2 divided by R squared. We can write this answer in terms of E. So the force is equal to K constant, which was 9 times 10 to the 9. Our charges are +1 and -1. And our distance is 0.53 times 10 to the negative 10 meters squared. So the distance itself is squared. When we write our answers out, we're going to express it in terms of E times E, or E squared. So including E squared, when you find your answer, type it in the field below. 3 charged particles are arranged in a line, shown below. Calculate the net electrostatic force on particle 3. This is the one on the very right, due to the other 2 charges. So let's take a look first at the direction of these charges. Are they going to be pulling on the charge, or are they going to be pushing it away? So the first charge, or the first force that we could talk about, are the force of 2 on 3. So if we start at the charge, we know that they are oppositely charged particles, so that it's going to pull inward towards the positive charge. So it's going to pull the negative towards it. This is the force acting on 3 by charge 2. The other force, however, it is further away, but it's also the same charge. So if it's the same charge, it'll be pushing it in the opposite direction. And this is the force on 3 by 1. So we're going to take these two separately. The first one, let's take a look at the force on 3 by 2. That's equal to K constant, so I know that's 9 times 10 to the 9. Q1 is -4 microcoulombs, so that's Q3. Q2 is +3 microcoulombs, and they're separated by a distance of 0.2 meters, and I know that distance is squared. So I know that towards the left, we got a positive times a negative. I'm going to get a negative value. Use your calculators to calculate the net or the force of these two between these two charged particles. The force on 3 by charge 1 is going to equal that same constant times the product of the charges. So again, that's a negative, or microcoulombs times the negative 8 microcoulombs divided by this distance squared. So this distance is 0.3 plus 0.2, so 0.5 meters, and that's squared. Calculate your answer. The total will be the combination of these forces, so we're going to add them up. We're going to get the force that's written in blue here plus the force that's written in red, force by charge 1. And we're going to get a net force, remembering that one of these forces is negative, though. So calculate the net force, and once you're finished, type it in the field below.